All right, our next topic is all about something called Sig Figs. And what Sig Figs get us is they end up helping us with our precision and the amount of numbers that matter. So if we go back to what we had looked at before, why do we use Sig Figs, right? It's because precision, especially in science and really in all of our lives, is something we need to deal with, something that we want, and something that if people aren't being precise, if they're not using these significant figures, they could easily lie to us or get really bad data that we'll talk about as we kind of go through this. That is just not true, and we don't want that, right? Especially being scientists. Maybe if we're politicians, we want to use this against people, but we're going to try not to. So going back to what we had just talked about, right? If we have two different rulers, right, which of these is most precise? The idea is that this one is more precise, even though they get us the same basic information. This one's more precise, right? Meaning that if we really want accuracy, if we want to try to get the correct answer, this would still probably be our best bet, even though we could potentially get the correct answer with this one too. And if we go back and we really remember that rule, the rule is you can only give me what the non-digital scale gives you plus one guess. So if we're going to do that, just to kind of reiterate, what is our best guess of what this ruler is going to give us? Well, if we look at it, we have a 2, we have a 1, we have a 3, right? And there are 10 marks in between. So that means we know each one is a 10th, right? And we can take an extra guess. So if we know each one's a 10th, and we are going up here, what is your best guess? Hopefully, you did something around that, right? 2.55. We know this, we guessed that. We know it, we guessed it. Okay? Where the this guy, can we do that well? We can't, because the only number we know for sure is the 2. We still want to take a guess. It's just not going to be as precise as our last guess. So the significant figures come in based on these rulers. And we're going to go over the rules, but I'll just tell you right now, this guy has 3 significant figures. This guy's only got 2. Okay, sometimes 2 is good, but generally the more significant figures we can actually use, the better. And significant figures always come down to the tools we use. Okay, they always do. The precision of your tool will tell you the number of numbers you can tell me. Okay, so let's take a look at this. This isn't a tool, but it really kind of is. If I owed you $12, but I didn't have anything lower than a $5 bill, what would I give you? Right? If I had 20s, if I had 10s, if I have 50s, if I have hundreds, and I owed you $12 for whatever, a pizza that you brought me, would I give you a 10 or would I give you 15? Those are my only options because my precision goes down to my $5 bill. Yes, if I had ones, I could give you exactly $12. If I had dimes and nickels and quarters, I could give you $12, but I don't. My precision is that $5 bill. So either I'm going to give you 10 and rip you off, or I'm going to be nice and I'm going to give you that $15 and say, hey, here's the tip. But again, this comes down to significant figures. The place value that we're working with the ones, and we're even more restrictive than the ones position because we only have part of that ones position, right? And so when we talk about significant figures, if you think about money, it generally helps you out a little bit. All right, so one more look. So we have our graduated cylinder here, and this again is one that's kind of hard and one you got to be careful on. So we have a graduated cylinder, and we're measuring this liquid right here, and we're always measuring at the bottom of the meniscus. So when we look at this, what are each one of these lines worth? Right, each one of these lines is worth 2, which makes it kind of hard. It's kind of like our $5 bill. Even though it's graduated, it's still not super precise. It's not as good as it could be. If those were ones, we'd be able to deal with this a little bit easier. But because there's not, what would our best guess be? Right? We know this is a 6. We know this is a 7. So this is 6.2, 6.4, 6.6, and 6.8. Can you guess 6.7? Can you guess 6.75? Can you guess 6.6? 6 or 6.2, right? What is the best answer here? And because the scale isn't as precise as we need to be, our best guess is really just like 6.7. These differences of 2 is kind of like our situation over here. Yeah, we understand we can get $1, but we don't have it. So it's really hard to do anything better than that. And so when we're looking at scales, you want to be very careful about which ones you use. But that's what significant figures are going to get us. Once we understand what significant figures are, which we're going to go about in this lesson, then we can go back and we can use our tools to really justify the numbers that you're going to give me. Okay, so let's look at the rules. I would take, jot down some of this stuff. I'm never going to ask you what rule number 1 is and rule number 5 is, but you got to be able to use them. All right, so basically anything that's not a 0 is always significant, right? We don't ever have to worry about them. They count no matter what they are, no matter where they are, and that just makes sense. So if we're looking at these, this guy, there's no zeros in it, so you would tell me that that guy has 3 significant figures. All right, this guy, a little bit different. There's a decimal there, and that's going to come into play. This guy's got 3 significant figures. All of those numbers matter. Whatever tool we were using to measure it, saying we measured to the nearest hundredth, we measured to the nearest ones, right? Those are all significant. This guy, right, there's 1, 2, 3, 4, 5, 6, 7. That guy's got 7 significant figures, and it's precise to the 10th. So when you don't see zeros, your answer is pretty easy. It's only when we get into zeros where significant figures play with our minds a little bit, and we just want to get these rules, right? And so the next rule is, let me get that guy out of the way. All zeros between 2 non-zeros are significant, right? I call this my sandwich rule. So let's take a look at some of those. So we don't have to worry about any of these zeros either. Zeros happen all the time. This guy between the 1 and the 1, we can't just get rid of it. It wouldn't make any sense, right? This guy is 101. I gave you $101. I gave you, my precision was down to the nearest dollar. If I get rid of that 0, do you really just want $11? Because that's what you'd be telling me. Okay. This guy, same thing. We can't get rid of either of those zeros. They're there. We didn't have a digit that was something other than a 0 to put there. All right, so those are both significant. So we'd have 3 significant digits here. We'd have 5 significant digits here. This guy, what do we got here? Again, it's still sandwiched. There's still something in front of it and behind it. So there we have 4 significant digits. All right, we are just precise to the ones position. That's good. And we went all the way up to the thousands. That's even better. All right, how about here? Now we get this decimal. Are these 2 significant? They are. Right? Because we have a 2 and a 3 here, great. And we have a 2 and a 3 there, great. All right, so those are still sandwiched. So in this case, again, just like rule number 1, any zeros that are between 2 significant numbers are significant, right? They matter. We can't get rid of them. All right, we need to record them is basically what we're saying. Okay, so let's get to rule number 3. Maybe. Come on, click me through. So rule number 3 is zeros in front of non-zero numbers are not significant, right? So non-zero numbers are basically 1 through 9. They're not significant, right? We call them placeholders, which you've heard before and you've used before, but sometimes we might think about them incorrectly. So what this means, eliminate with scientific notation, if you could get rid of zeros and you don't need them in scientific notation that we talked about earlier, those are called placeholders, right? And they can be anywhere in a number, and we'll talk about the ones in front specifically. So when we look at this guy, there's a 0 in front of the 554, right? If that decimal wasn't there, if we just kind of cover it up, would it make any sense to put a 0 there? Absolutely not, right? You wouldn't put a 0, 554. But what we could confuse is when we put this down there. Now, we usually always put a 0 in front, so it kind of shows us that the decimal place is there. But in this case, how many significant figures do we have? We have 3. Okay, that 0 doesn't count. It's a placeholder. It's showing us where the ones position is, but we're precise down to the thousands, right? Here, again, we are precise down to the thousands. So both of these could have been using the same scale. They could have been using the same machine to get this data. This guy just wasn't as big, okay? So the real question is, we know this one doesn't count. Do these 2 count? And the answer is no, they don't. right? They do not count. They're placeholders. They're important, but we couldn't just randomly stick a number in there and change the fact that this is a 9, right? So think about that. These are not significant. So we go to all these. None of these are significant either. So this guy has 3, because this guy's the sandwich rule, right? He's rule number 2. These are 3 significant figures. So we have 3 here, we have 1 significant figure here, and we have 3 significant figures here. So placeholders are never significant. Are they necessary? Yes, they're just not significant. You can change all of these into scientific notation and get rid of all those zeros that are happening in front. All right, and we'll probably try to do that together. All right, so rule number 4 is the big one. Rule number 4 is where people get confused, and I will try to help you out. And really, it's a 2-part rule. Okay, I try to simplify it. So given this, zeros are significant when both of the following are given. Okay, zeros are significant when you can do both of these next 2 things, but it's got to be both, right? So they are after a 1 through a 9, right? So they're after a digit that we already classified as significant. That's checkbox 1. If you can say that, you're good. Okay, but you also have to do this. There's got to be a decimal point somewhere, anywhere in the number. Okay, so they got to be after a 1 or a 9, 1 through a 9, sorry, and there's got to be a decimal place somewhere. Okay, so let's try these 2 out. So let's look at it. Okay, we do not get to start counting until we hit our first 1 through a 9. So this 0, just like on the last page, it doesn't count. Okay, it does not happen before, or I should say after a 1 through 9. So we know we don't start counting our significant figures till we get right here. So here's our first significant figure. Here's our second, no thought process, right? Does this 0 count? And it does. It is both after a 1 through 9. It's after actually 2 of them, right? And there's a decimal somewhere in the answer. The decimal is right here. It wouldn't matter where it is, and I'll prove that when we do a live session. It wouldn't matter where it is, but those 2 count. So if I were to ask you how many significant figures do we have, this guy's got 3, right? 1, 2, 3. This guy over here, all right, how many significant figures does it have? We're not worried about that 0 at all because that's the sandwich. So we know for sure we have 4. So the real question is, do these 2 count? Well, are they after a 1 through 9? They are. Check. There's a 5 right there. And is there a decimal somewhere in the answer? Check. So we have check, check. So this guy would have 6 significant digits. Try 2 more. All right. This guy, we have a significant digit, right? A 4 with 3 and a 5. Good. So we for sure have 3. So now we got to check our zeros. They are after a 1 through 9. Perfect. Is there a decimal anyplace? No, there's not. There's no decimal. And so if I wanted significant digits, this guy also, just like this one, only has 3. These digits would be called placeholders. They're necessary, but again, we can get rid of them. I can turn this into 4.35 times 10 to the 4th, and it means the exact same thing. I don't need those zeros there. Okay? We will not miss them. And finally, this guy. How many of those guys are significant, right? How many of those guys are significant? And the answer is 3, right? None of these zeros count because they don't come before, or they come before the first significant digit. They do not come after a 1 through 9. So here's our first 1 through 9, right? And there's another one, and there's another one. So here are 3 significant digits, okay? And so the idea of this is this rule shows us the precision. It shows us, hey, do the zeros matter or don't they? This guy was only precise to the hundreds, right? Maybe I only had $100 bills. That's as good as I could do. I might have owed you some change. I might have owed you $50 more. Couldn't give it to you. This guy was precise to the thousands. This guy was precise to the hundreds. This guy was precise to the 100,000s, right? They're all different, but just because of precision, they don't always tell you the number of significant digits, but we need to look at both all the time. All right. Let's look at the last rule. These are things that have unlimited significant figures, right? Counted numbers. So if we see there's 12 people in the room, that is always, always, always going to be true. We're not cutting somebody in half, right? And so counted numbers, that is precise. We could say there's 12.00000000000 people in the room, and we'd always be right. So counted numbers have unlimited significant people. Oh man, that was good. I didn't even know that was going to pop up, even though I wrote it. Number of hairs on your head. You can count them all up and you would always be right. So those have unlimited significant figures, meaning when we go and do the math, those are not going to affect your math at all, counted numbers. All right. Or let me get this out of the way. Define quantities, right, which we're going to talk about these next week. They're equalities, ratios, fractions. Basically, when we do this thing called dimensional analysis, we're going to talk about these guys, right? So define quantities, things that we know. Okay, so they might like 12 bananas in 1 dozen, right? So 12 is equal to a dozen. If we can put equals in there, this is just another way of kind of giving it a counted number. Or 60 minutes per hour, or 60 miles per hour, or anything like that. Yes, there is a 1 here, right? But this ratio right here, knowing that it's perfect, all right, something that we know, something that's an equality, they're equal to each other, we wouldn't want that 1 to limit our answer. And so this guy we wouldn't care about. It would be unlimited sig figs. One more. Okay. How about 1,000 meters per second? Get out of the way. Right? 1,000 meters per second. This guy, if we're giving the meters per second, if we're saying that is something that we recorded, we would say it has a defined quantity, and we could write that out, right? So if 1,000 meters is equal to 1 second, all right, we know that in this case. That might be a tough example, because if we just looked at that number, we'd say it has 1 significant digit. But as we're doing our math, this would never come out, because this probably wasn't something we measured. Okay, so unlimited significant figures. All right, so I want to end with this. Can you give me the answers to these 3? And we'll see how you do, and we will come up with them. So take a look, try these out, go back and look at the rules. Hopefully you took notes. You can justify which of these has the proper number of significant figures. All right, good job.